सब लोगों को नमस्कार एंड मैं उम्मीद करता हूँ आप सब लोगों की तैयारी अच्छी चल रही है। गुड इवनिंग शाहरुख अंसारी, गुड इवनिंग एवरीवन। आज हम पावर इलेक्ट्रॉनिक्स के PYQs जो हैं उनको हम सोल्व करेंगे। काफ़ी डिमांड थी आप लोगों की कि PYQs जो है उनको आप सोल्व करवाइए, क्योंकि जनरली पावर इलेक्ट्रॉनिक्स के जो PYQs हैं मेनली जो लास्ट के 3-4 ईयर्स के वो आपको मेरे अवेलेबल नहीं थे। मैं आज आपको PYQs कराऊंगा एंड मैं हिंदी इंग्लिश दोनों में ही कराऊंगा सारी, सो दैट आपको दिक्कत ना आए, कोई भी दोनों ही तरह के स्टूडेंट्स को समझ सके, दोनों ही तरह के स्टूडेंट्स मुझे कैच कर सके। इम्पॉर्टेंट है, कोई फॉर्मूला नहीं लगाएंगे, नो नीड टू रिमेंबर एनी फॉर्मूला। और आप देखिएगा कि जब मैं पढ़ाऊंगा, जब आपको सोल्व करवाऊंगा, मैं भी कोई फॉर्मूला नहीं लगाऊंगा, बिकॉज अगर मैं कोई फॉर्मूला लगाता हूं इट मीन्स आप फॉर्मूला डिपेंडेंट हो गए, आप भी फॉर्मूला आपको याद करना पड़ेगा। बट मैं कोशिश करूंगा कि आपको कोई फॉर्मूला नहीं याद करना पड़े, इस तरह से हम चीज़ों को सोल्व करें। तो आई होप आपको सेशन जो है कंसेप्चुअली चीज़ों को सोल्व करेंगे और सेशन आपको अच्छा लगेगा और आपको कुछ सीखने को मिलेगा। ओके, सो लेट्स स्टार्ट द सेशन गाइस। शुरू करते हैं, बट स्टार्ट करने से पहले आप लोग इसको सब्सक्राइब कर ले चैनल को, बिकॉज ये इंपॉर्टेंट है। जिन लोगों ने भी सब्सक्राइब नहीं किया है प्लीज़ इसको सब्सक्राइब करें भाई, और लाइक कर दीजिएगा सेशन को। अगर आपने अभी तक लाइक नहीं किया है तो बेल आइकन प्रेस कर दीजिएगा, आपको नोटिफिकेशन मिलते रहेंगे। ये हमारी गेट एमर सीरीज एक चल रही है पैरेलल में, ये तो PYQ सीरीज है, गेट एमर सीरीज भी हमारी चल रही है। तो मेक श्योर कि आप जो है गेट एमर सीरीज में कंसेप्ट को हमसे आप समझ सकते हो, सीख सकते हो। तो उसमें मेरे पावर इलेक्ट्रॉनिक्स के सेशंस आने वाले हैं, उसमें मशीन्स के भी सेशंस मैं लूँगा, तो वो भी आप जो है मेरे साथ करेंगे। ये एक सेशन आ रहा है 20 दिसंबर को जोशी सर के साथ, ये आप लगा सकते हैं। और मेनली जो 2024 के स्टूडेंट हैं, आपके जो जूनियर्स हैं, उनको आप जरूर राय दीजिएगा, जरूर बताइएगा। ओके, ये जो सीरीज हमारी चल रही है PYQ सीरीज है, जिसमें लास्ट 5 ईयर के जो क्वेश्चंस हैं उनको हम डिस्कस करेंगे। तो 2018 से लेके 2022 तक जो अभी तक PYQ क्वेश्चंस पूछे गए हैं पावर इलेक्ट्रॉनिक्स में, उनको आज मैं डिस्कस करूंगा। ये टाइम टेस्ट सीरीज का है दोस्तों, तो टेस्ट सीरीज स्टार्ट कीजिए, अपनी टेस्ट सीरीज ज्वाइन कीजिए। बायजूस एग्जाम प्रेप आपको टेस्ट सीरीज दे रहा है, कोई ज़्यादा कॉस्टली भी नहीं है और बिल्कुल एक एग्जाम ओरिएंटेड टेस्ट सीरीज आपको मिल रही है। तो मेक श्योर कि आप ये टेस्ट सीरीज जरूर ज्वाइन करें। इसमें आपको काफ़ी सारे टेस्ट मिल जाएंगे, वर्चुअल कैलकुलेटर मिलेगा, बिल्कुल इंटरफेस जो IIT का होता है बिल्कुल वैसा ही आपको मिलेगा। तो एकदम आपको बढ़िया तरीके से आप इसमें तैयारी कर सकते हो। ठीक है, एक ऑल इंडिया ओपन मेगा मॉक टेस्ट जो है हमारा गेट 2023 के लिए, उसके लिए आप रजिस्टर कर सकते हो, नीचे लिंक दे रखा है। ठीक है, तो आप लिंक पे जाइए और वहां पे आप रजिस्टर कर सकते हो। चलिए दोस्तों स्टार्ट करते हैं। तो सबसे पहला क्वेश्चन 2022 मतलब 2022 से हम स्टार्ट कर रहे हैं। तो जरा देखिए पहला क्वेश्चन क्या है। फर्स्ट क्वेश्चन में अगर आप देखेंगे तो फर्स्ट क्वेश्चन में आपको सिंपल डिवाइस के बारे में पूछा है। मैं आराम से चलूंगा, मैं स्लो चलूंगा, सो दैट एवरीबडी कैन अंडरस्टैंड एंड एक तरह से हर चीज आपको समझ आती हुई चले। सो विल स्टार्ट फ्रॉम द बेसिक एंड विल स्टार्ट स्लो। ओके, सो लेट्स रीड द क्वेश्चन नंबर 1। ए चार्जर सप्लाइज 100 watt 20 volt 100 watt to 20 volt फॉर चार्जिंग द बैटरी ऑफ ए लैपटॉप। सो एक चार्जर है जो 100 वोल्ट सप्लाई कर रहा है, 100 वोल्ट सप्लाई कर रहा है 20 वोल्ट की बैटरी को। ओके, द पावर डिवाइसेस यूज्ड इन द कन्वर्टर इनसाइड द चार्जर ऑपरेट एट ए स्विचिंग फ्रीक्वेंसी ऑफ 200 किलोहर्ट्ज। यहां पे 200 ये प्रिंटिंग मिस्टेक है, सो 200 किलोहर्ट्ज। सो इट इज ऑपरेटिंग एट 200 किलोहर्ट्ज। Which power device is best suited for the purpose? So 200 किलोवाट के लिए कौन सा डिवाइस सबसे बढ़िया आपको रहेगा? और ये 1 मार्क क्वेश्चन था दोस्तों। कौन सा 200 के लिए अगर आप देखोगे तो अगर मैं आपको बताऊं BJT, सबसे पहले BJT अप टू 20 किलोहर्ट्ज तक होता है। BJT में पावर लॉस कम होते हैं, मतलब जब कंडक्शन करता है BJT, जो कंडक्शन लॉसेज होते हैं वो कम होते हैं, बट इसमें स्विचिंग जो है वो फास्ट नहीं कर सकते हो आप। यू कैन ऑपरेट इट अप टू 20 किलोहर्ट्ज। ओके, मोसफेट का जो ऑपरेटिंग फ्रीक्वेंसी होती है वो इवन 500 किलोहर्ट्ज तक भी हो सकती है, बट अगेन उसमें कंडक्शन लॉसेस जो हैं वो थोड़े से ज्यादा हो जाते हैं। सो हम मोसफेट को यूज कर सकते हैं यहाँ पे थायरिस्टर को तो बिल्कुल भी नहीं, क्योंकि थायरिस्टर में तो कम्यूटेशन सर्किटरी बहुत ज्यादा आ जाएगी। तो थायरिस्टर तो बिल्कुल ही आप थायरिस्टर मेनली वहां पे यूज करते हैं जहां पे हाई पावर हो। यहाँ पे पावर ज्यादा हाई नहीं, आप देखिए 100 वोट की पावर है, तो 100 वोट में थायरिस्टर लगाने की जरूरत नहीं है। आईजीबीटी अगेन 50 किलो हर्ट्ज तक आप यूज कर पाओगे, बिकॉज आईजीबीटी की जो रेंज होती है वो बीजेटी से ज्यादा होती है, मोसफेट से कम होती है। तो इट मींस यू कैन से कि यहाँ पे हम मोसफेट को ज्यादा वैल्यू करेंगे, ज्यादा मतलब ज्यादा सही अगर कोई मैं अगर बताऊं तो मोसफेट ज्यादा सही रहेगा। ओके, सो एक सिंपल क्वेश्चन था ये, 1 नंबर का क्वेश्चन था मेरे ख्याल से, बहुत ही इजीली आप इसको सोल्व कर सकते हो। मैं एक बार जरा ओरिजिनल फाइल भी खोल लेता हूं, सो दैट कोई मिस्टेक हो अगर तो वो भी हम पकड़ पाएंगे, एंड उसको फिर मैं साथ साथ रेक्टिफाई करता हुआ चलूंगा। ओके, सो एक बार मैं ओरिजिनल फाइल भी खोल लेता हूं दोस्तों, सो दैट आपको भी दिक्कत ना आए, मुझे भी दिक्कत ना आए। कोई स्टेटमेंट में कई बार क्या होता है, गलत स्टेटमेंट लिख दी जाती है, प्रिंटिंग मिस्टेक हो जाती है। ओके, तो चलिए नेक्स्ट क्वेश्चन जरा देखिए, क्वेश्चन नंबर 2, ए सिंगल फेज फुल ब्रिज डायोड रेक्टिफायर। सबसे पहले आप जरा देखिए, फुल ब्रिज डायोड रेक्टिफायर इज देयर, feeds a resistive load. Now the load is resistive of 50 ohm from 200 volt 50 hertz single phase AC supply. The diodes are ideal, then the active power in watts drawn by the load. How much active power is drawn by the load? Now, तो अगर आप देखें तो मेरे पास आपको जो डिवाइस जो आपको दे रखा है वो डायोड रेक्टिफायर है। ओके, ये मेरे पास एक डायोड रेक्टिफायर हो गया, एंड नाउ द लोड इज प्योरली रेजिस्टिव। नाउ द लोड इज प्योरली रेजिस्टिव। Okay, now the load is purely resistive, and here we have the source. We need to calculate what is the active power supplied by the source या drawn by the load. So जो resistance होता है वो जितनी भी power consume करेगा, that is called active power. Okay, the power consumed by the resistor is itself an active power. वही power यहाँ से active supply होगी. So you can calculate the power absorbed by the resistor. The power absorbed by the resistor itself is called the active power, or you can say in watt, because watt में तो active power ही होती है. So how to calculate this power? First of all, just draw this output voltage. In case of rectifier, in case of full bridge rectifier, the output voltage will look like this. Output voltage will look like this, and this peak value will be Vm. Okay, this will be Vm. Now, to calculate the power lost in this resistance R, what I need to do is, I can write that V naught T RMS square upon R is the power lost in this resistance R. Now what is this V naught RMS? Now we need to calculate the RMS value of this output voltage. How to calculate the RMS value of this output voltage? It's very simple. The peak value, what is the peak value? Peak value 200 root 2 है, 200 root 2. 200 root 2 is the peak value. Okay, इसकी पीक वैल्यू 200 रूट 2 है। नाउ व्हाट इज द आरएमएस वैल्यू ऑफ दिस सिग्नल? आरएमएस, इसकी जो आरएमएस वैल्यू है वो 200 ही है। आरएमएस इज 200 इटसेल्फ, डिवाइड बाय रूट 2 यू कैन कैलकुलेट द आरएमएस वैल्यू इन फुल वेव रेक्टिफायर। ओके, सो द आरएमएस वोल्टेज अक्रॉस दिस रेजिस्टेंस इज 200 वोल्ट। नाउ व्हाट आई नीड टू डू इज आई नीड टू कैलकुलेट द पावर। सो द पावर विल बी 200 स्क्वायर V naught T RMS square upon R. R is 50 ohm. So this way you can calculate the power lost, or the active power supplied by the source, or you can say the power drawn by the source. Okay, so it's very simple. Now the question is, how I have written that the RMS value will remain same as the RMS of the source, because the source voltage is pure sine wave. Source voltage मेरे पास pure sine wave है, and I told you जब भी आपको RMS निकालनी होती है, whenever you rectify this signal, full wave rectification पे, whenever you full wave rectify it, RMS value will not change. So अगर आप इसको rectify कर देंगे, then the wave will look like this, and the RMS value will remain same. So the RMS value of this signal is 200 volt. It is given in the question. So the RMS value of the rectified signal will also be 200 volt. Okay. So now you can say that across this resistance, RMS value is 200 volt. 200 square upon 50 is called the active power absorbed by the load. I hope you understood it. Let's move to the next question. In the next question, question number 3, the voltage at the input of AC-DC rectifier. So there is an AC-DC rectifier, and the input voltage is provided to us. Input voltage is pure sine wave, and omega is also given as 100 pi. The input current is also provided to you. Now what I need to do is find the input power factor. We need to calculate input power factor. How to calculate input power factor? Input power factor will be equal to active power divided by apparent power. active power divided by the apparent power is called the input power factor. Okay. Switching frequency means, switching frequency means on and off frequency. Switching frequency means on and off frequency. You are asking about this question. Okay, the switching frequency is 200 kilohertz. It means on and off, wherever the switch is connected, at that point the switch is turning on and turning off. So at what frequency it is turning on and off? Okay, that is called switching frequency. Now let's come to this point. So I need to calculate the input power factor. Good evening, Yaswanath. Good evening everyone. So now I need to calculate input power factor. What is the meaning of input power factor? Input power factor is active power divided by apparent power. So you can say that from the input side, I need to calculate how much apparent power is supplied and how much active power is supplied. The input side is pure sine wave. Input side is pure sine wave, and the current has harmonics. Current has harmonics. So how to calculate the active power supplied by the source? So active power will be equal to, you can apply Parseval relation, 1/2 into, there is no DC component in this voltage and in this current. So you can say that there is only one component in voltage. Now the active power will be supplied only because of the same frequency component. In voltage source you have omega frequency component. In the current also you must have that omega frequency component. Then only it will supply the active power. Okay. So now the active power supplied will be 1/2 peak value of this voltage, which is 230√2, into peak value of this current only, because this current will participate in active power. Same frequency component will participate in active power. Okay. So the max value of this current is 10 into cos of angle between them. What is the angle? What is the angle between them? Here the angle is 0. Here the angle is 60 degree. So you can say cos 60 degree. Okay. So this will be the active power. This will be the active power. You can calculate this active power as cos 60 is 1/2. So you can write it like this: 2300√2 divided by 4. I hope it is clear to everyone. Okay. So this much of what is the active power? This is the active power supplied by the source. Now what is the apparent power? To calculate the apparent power, what I need to do is I need to multiply the supply voltage RMS and the supply current RMS. You just calculate the RMS value of this supply and the RMS value of this current, the supply voltage and this current. Okay, and then multiply them, you'll get the apparent power. So the apparent power will be equal to, what is the apparent power, guys? RMS value of this supply voltage is 230. RMS value of this supply voltage is 230. And what is the RMS value of this current? RMS value of this current is root of, you can apply Parseval to calculate the RMS value, root of DC component. There is no DC component in this current source. So if there is no DC component, then 0 square plus 1/2 AC component square. So here the AC component is 10. So 10 square is 100, plus here the AC component is 4, 16, plus here the AC component is 9, 3 square is 9. Okay. So this way you can calculate the RMS value of the current. So this is the RMS value of the current. Multiply by the RMS value of the voltage. This will be my apparent power. So if you calculate this, you'll get 230 into root of, what is this? What is this, guys? 125 divided by 2. Root 125/2. I hope it is clear. This is my apparent power and this is my active power. So what I need to do is now, we need to calculate input power factor. So input power factor is this ratio. Input power factor is active divided by apparent. So active is 2300√2/4 divided by apparent. Apparent is 230√125 into √2. Okay. Now you can calculate this, cancel with 10. Here the 230 and 2300 divided by 230 is 10. So the numerator will be 10 into √2 into √2 is 2 divided by 4 √125. Okay. This is my input power factor, guys. Now you can calculate this decimal value. So let me cancel it. So this will be 5. So you can say 5 upon √125. You can write it like 1 upon √5. Okay. So 1 upon √5 is the input power factor. Now the thing is, The thing is, what you need to understand is, don't try to calculate the decimal value in between the question. Because there are many students, what they do is, they try to calculate the decimal value of this active power and the decimal value of this apparent power. It will make you slow, so don't do it. What you can do is, you just write it like this, in the form of numerator and denominator, okay? Similarly, in apparent power, don't calculate the decimal value. At the last step, you calculate the decimal value. It will make you fast, okay? Your calculation will be fast and you don't need to, the time will be saved, okay? So I hope you understood it. So this much is the input power factor. You can calculate this value. I hope it is clear to everyone. It's 0.455. Okay, Yaswant. Thank you. Thank you, Yaswant. So it's 0.455 as per Yaswant. I hope it is clear, it is correct. And let's move to the next question. So it's very easy question. This question was based on Parseval relation. Okay, let's move to the next question. Yes, in this question, what is given is, it's a semi-converter, single phase semi-converter. For the ideal AC-DC rectifier shown below, the load current magnitude is 15 ampere. Okay, this current magnitude is given as 15 ampere. Okay, and it remains constant. It's ripple free. Ripple free means it's constant. So the load current is constant. The thyristor are fired with a delay angle of 45 degree. Alpha is given as 45 degree. Okay, alpha is provided to us, which is 45 degree. The amplitude of fundamental component of the source current in ampere. We need to calculate the fundamental value of this source current. Now, there are some students who think that now I need to apply the formula. No, sir. You don't need to apply any formula. There is one thing that is called quarter wave symmetry. If you know how to apply the quarter wave symmetry method, then you can easily calculate the fundamental component. Now, what is that quarter wave symmetry? Okay, let me tell you quarter wave symmetry. But before that, I need to draw the supply current IST. I need to draw the wave shape of supply current IST, and it is not time consuming. Let's try to plot the wave shape of supply current IST. First of all, this is my supply voltage VST. Okay, this is my VST, and this peak value is Vm. 0, pi, 2 pi, 3 pi. Now, the firing angle for this T1, let's call it D1. This is T2, let's call it D2. Firing angle for T1 is 45 degree. Let's call it alpha. This is alpha. This is pi plus alpha. This is 2 pi plus alpha. Now, at alpha, you can see that thyristor T1 will start conducting. If I need to plot IST. But remember, these two diodes, D1 and D2, in which configuration these two diodes are connected? They are either they are in common anode or common cathode. Now, what is the configuration? If you look at carefully, their anode is common. Their anode is common. Let's say this voltage is 0. Let's assume that this is grounded. So this voltage will become VST. Okay? And whenever two diodes are connected in common anode configuration, whenever two diodes are connected like this, they have common anode. They have common anode. Whenever two diodes are connected in common anode configuration, two diodes are connected like this, okay? Now, the diode which has the lowest voltage, on its cathode will conduct. The diode which has the lowest voltage on cathode will conduct. Now, tell me, in the first half cycle, this is 0 and this is positive. So, which diode has the lowest voltage? Obviously, D1 has the lowest voltage. So, it means out of D1 and D2, you don't need to fire anything. Out of D1 and D2, you can say that D1 will conduct in the positive half cycle. You don't need to look at the firing angle, okay? For D1, D2, you don't need to look at the firing angle. So, from 0 to pi, you can say that D1 will conduct. Let me change the color. Let me write it in a different color. So, from D1 to D2, okay? Yes. From D1 to D2, you can say that up to this point, from 0 to pi, D1 will conduct. We know that. Because from 0 to pi, this is 0, this is positive. 0 is less than the positive value. That's why you can say that diode D1 will conduct between 0 and pi. Now, let's come to pi and 2 pi. Between pi and 2 pi, which diode will conduct? First of all, I am looking at the diode only. Which diode will conduct from pi to 2 pi? From pi to 2 pi, VST is negative. This is negative and this is 0. Now tell me, which diode will conduct? Obviously, D2 will conduct. So from this point to this point, D2 will conduct. Now, from this point to this point, again, D1 will conduct, okay? Yes, so Rakesh sir is here and सब लोगों के आपके चहेते जो है सर से आप मुलाकात करें तो दोनों ही आईएससी से आप भी सर आपका कौन सा सर ईयर रहा था आईएससी
11 से 13
11 13 ओके तो मैं आपका सीनियर रहा हूँ सर
आपका 12 ना आई थिंक
जी सर
ओके ग्रेट
ओके सो
बट सर ये थोड़ा सा मेरे को बच्चों का समझ नहीं आ रहा लेकिन पीवाईक्यू एंड बच्चे हमेशा अटेंडेंस के मामले में ना दे आर ऑलवेज बट इट इज द कोर सब्जेक्ट सो आई बिलीव जो भी लोग you know they are watching right now they are very serious and I hope many more will be watching the recording क्योंकि पावर इलेक्ट्रॉनिक्स एक ऐसा सब्जेक्ट है जो
बहुत इंपॉर्टेंट है
एंड मेनी पीपल जस्ट लीव इट अप ओके लेकिन टॉपर्स लीव नहीं करते तो गाइस यू आर डूइंग अ ग्रेट जॉब जो लोग है ना द ग्रेट जॉब
जी सर सर करता हूँ फिर मैं
बिल्कुल गाइस ऑल द वेरी बेस्ट कीप प्रिपेयरिंग वेरी हार्ड कल मैं आऊंगा टुमारो कल डिजिटल का सेशन है इन लोग का
जी
तो आज पावर इलेक्ट्रॉनिक्स एंड ईडीसी का चल रहा है तो टुमारो विल हैव डिजिटल पीवाईक्यू गाइस वैसे इलेक्ट्रिकल के लिए डिजिटल का वेटेज थोड़ा कम होता है इलेक्ट्रिकल का काफी कम होता है राइट बट इलेक्ट्रिकल इलेक्ट्रॉनिक्स दोनों का एक साथ कवर करूंगा उस सेशन में वेरी गुड इवनिंग ऑल गाइस
एंड सर आप मेरे सीनियर हैं बाय द वे मेरा 12 14
12 to 14 okay ठीक है सर right now we are colleagues that is more important ISC is the first now okay guys bye all the very best thank you sir
okay sir okay thank you so guys let's come to the topic so I told you that from 0 to pi D1 will conduct because D1 has the positive voltage so here you have the positive voltage and this voltage is 0 so you can say that this is positive this is 0 so you can say that D1 has the lowest voltage so D1 will conduct between 0 and pi. Now from pi to 2 pi, D2 will conduct. If you look at from pi to 2 pi, this voltage is negative, this is 0. So if it is negative and it is 0, then D2 will conduct because D2 has the lowest voltage. Now again from 2 pi to 3 pi, D1 will again conduct. So you can say that if you are looking at the diodes, then it's very simple to analyze. Diode will not look at the firing instant. Now let's come to thyristor. T1 will start conducting only at this instant. So you can say that from alpha onwards, T1 will conduct. That's for sure. In the upper group, T1 will conduct. And in the lower group, D1 is conducting. So you can say that from this alpha point onward, D1 will start conducting. So you can say that from this point onward up to pi, T1 and D1 will conduct. T1 D1 is conducting. If T1 and D1 is conducting, you can say that the output voltage will be same as the supply voltage because this positive VST will connected here and the zero voltage will connected here. So you can say that the output voltage will be same as the supply voltage. Okay, so the output voltage will be same as the supply voltage from alpha to pi. Now from pi to pi plus alpha, if you look at pi to pi plus alpha, what will happen? From pi to pi plus alpha, T2 is not conducting because T2 is not fired yet. So now pi to pi plus alpha, D2 start conducting. D1 is changed to D2. So you can say that from this interval and up to this interval, pi to pi plus alpha, in diodes, D2 will start conducting. And in thyristor, T1 will keep on conducting because T2 is not started yet. So you can say that in the diodes, D2 will keep conducting. Now D2 will start conducting from pi onwards and in the thyristor, T1 will keep conducting. Okay, T2 will not start. T2 will start at pi plus alpha. So you can say that the current will freewheel. And the output voltage will remain 0. Now again from this point to 2 pi, what will happen guys? From pi plus alpha to 2 pi, T2 and D2 will start. Because in diodes we have D2 and in thyristor we have T2. So you can say that now T2, D2 will start conducting. So the output voltage will look like this. Okay. And then from 2 pi to 2 pi plus alpha, it's like this and then like this. This is my output voltage guys. This is the freewheeling period. During this interval, T1, D1 will conduct. During this interval, T2, D2 will conduct. T2, D1 will conduct. During this interval, T1, D2 will conduct. Okay. So it's a freewheeling. During this interval, there is a freewheeling between D2 and T1. Okay. I hope you understood it. How I have plotted this output voltage wave. Now let's come to supply current. If you want to plot the supply current, what will be the supply current? Now you can see that from alpha to pi, T1, D1 is conducting. T1 and D1 is conducting. It means you can say that this constant current I, 15 ampere, will flow like this. So you can say that the supply current will be positive. From alpha to pi, the supply current will be positive and it will remain at 15 ampere. Okay? It will remain at 15 ampere up to pi. Now from pi to pi plus alpha, supply current will be 0 because there is a freewheeling action going on. Okay? So from pi to pi plus alpha, current will be 0. Okay? Supply current will be 0. Pi to pi plus alpha. Now from pi plus alpha to 2 pi, T2 and D2 are conducting. If T2 and D2 are conducting, this 15 ampere will flow through D2 and the supply current will be negative now. Supply current, this 15 ampere will flow through D2 and will come via T2. Okay? So you can see that the supply current will be negative. So you can say this current will be minus 15 ampere. Is it fine? This will be minus 15 ampere. Now from 2 pi plus alpha, it is like this. Okay? So this will be the wave shape of current, IST, source current. Now the question is, what is the fundamental peak value, the amplitude of the fundamental component? Now I need to apply the quarter wave symmetry because I don't know any formula. I don't remember any formula. Sir, we did not connected freewheeling diode. Then how we have put current free? Okay, yes, one. Yes, actually you haven't connected freewheeling diode, but there is a freewheeling action here. Why there is a freewheeling action? Let me tell you guys. Because I told you from 0 to pi, D1 will conduct for sure. And then from pi to 2 pi, D2 will conduct. First of all, clear about these diodes. Okay? First of all, clear your concept about these diode. Diode will not look at the firing instant. So you can say that from 0 to pi, D1 will conduct, and from pi to 2 pi, D2 will conduct. That's for sure. That's final. Now, let's come to the Thyristor. Let's come to the Thyristor and let's look at the firing instant because the Thyristor will conduct after firing. So you can say that at alpha, T1 will start conducting. At pi plus alpha, T2 will start conducting. At 2 pi plus alpha, T1 again will start conducting. Now, start with alpha. Let's start with alpha. Okay. At alpha, T1 start conducting. So you can say that in the upper group, T1 is conducting from alpha onwards. And in diodes, we have D1. So now T1 and D1 is conducting. So current is coming like this. Okay. So the load current hai, that is coming from the source like this. Okay. Up to pi. What will happen at pi? At pi, Thyristor T2 is not turned on. Thyristor T2 is not turned on. But diode will switch to D1 from D1 to D2. It will switch from D1 to D2. So at pi, what will happen is diode will change. So you can say that now T1 is still conducting because T2 is not there. Na? T2 will get fire at pi plus alpha. So after pi, from pi to pi plus alpha, if you look carefully, from pi to pi plus alpha, you can see that T1 is still conducting because T2 is not fired yet. T1 is conducting, but in diodes, it's D2 which will start conducting. So D2 will start conducting. So you can say that T1 and D2 are conducting, and T1 and D2, if you look at carefully, it will be sorted. It means the load will be sorted. So the output voltage will remain 0 and the current will freewheel like this. Current will not go via supply. Okay, so there is an inbuilt freewheeling action here. There is no freewheeling diode, but still there is a freewheeling action. Have you understood? Yeah, yes, one. Tell me, have you understood this? Tell me, guys. I hope you understood this concept. So there is an inbuilt freewheeling action here. Okay. Now, this is my output voltage shape and this is the current wave shape. I need to calculate the fundamental component of this current wave shape. Now, how to calculate the fundamental component of this current wave shape? If you know the quarter wave symmetry, then it's very easy. The amplitude of this wave, fundamental amplitude, you can say the fundamental component of the current signal and the amplitude of the fundamental does not depend on the origin. It does not depend on the origin, okay? The amplitude of the fundamental component does not depend on the origin, whether you have taken origin here or somewhere other position. Okay, it doesn't matter about the amplitude does not care about the origin. Now, look at this. Look at this wave carefully. What I do is, this is 0, this is alpha, this is pi plus alpha. Now you can see that during this alpha range, output voltage, supply current is 0. From pi plus alpha, from pi to pi plus alpha, again it is 0. So if somehow I try to make the fundamental component, let's say I try to try to draw the fundamental component of the current, then the fundamental current will be, it should be symmetric, na? So now how to make it symmetric? It's very simple. The fundamental, if I make the symmetric, like a fundamental wave, if I make the symmetric, then it will start from alpha by 2 and it will end at pi plus alpha by 2, okay? This will be my fundamental wave. If I try to make it symmetric, if I try to make the fundamental wave, if I try to make symmetric, then it will look like this, okay? This will be my fundamental wave. Now, you will ask me, sir, how you have plotted this fundamental wave? It's a common sense. It's a common sense. You can see that in a fundamental component of the sine wave, you have the positive pulse, and the positive pulse should be symmetric about this wave, no? Because the wave is symmetric. You can say that from 0 to alpha, it's 0, then alpha to pi, it's positive, and then from pi to pi plus alpha. So every alpha gap is 0, and every pi minus alpha gap is 15. So it's a symmetric wave. Now, if the wave is symmetric, then you can plot the fundamental like this. I mean, the zero crossing should be in between the points. Now, how to calculate its amplitude? If I assume that this is the origin, this alpha by 2 is the origin. This point, if I assume that this represents the origin, then this point will represent alpha by 2 point. If this point represents the origin, then this point will represent alpha by 2, and this point will represent pi by 2. If I call this point at origin, then this point will be pi by 2, half wave, and this point will call this point as pi. This point we will call pi. This will be pi by 2, and this is 0. So if you know the concept of quarter wave symmetry, what you have done is you have assumed the origin here. If you have assumed origin here, then the wave will become quarter wave symmetric. How it will become quarter wave symmetric? Let me tell you guys. If you plot the negative half also, now you can see that if the origin is at the red line, then the wave is odd signal. The wave become odd. If the origin is here, let me erase this point. Let me erase this. Now you can see that. Now you can see that this become the origin, and this wave is odd, and it contain odd half wave symmetry. So if the signal is odd and contain odd half wave symmetry, it will become quarter wave symmetric. I hope you understood it. So if this is the origin, then this point will become alpha by 2. This point will become alpha by 2. And this point will become pi minus alpha by 2. And this point will become pi by 2, okay? Now it's easy to calculate its fundamental component. How to calculate the fundamental component? Let me tell you, you can apply the quarter wave symmetry. Using quarter wave symmetry, you can say that the peak value of the fundamental is, if you know the quarter wave symmetry, then you can easily apply this. 4 by pi from alpha by 2 to pi by 2. We are looking only under 1 quarter. We are looking only under 1 quarter. Under 1 quarter, from 0 to alpha by 2, the amplitude is 0. So no need to write it. From alpha by 2 to pi by 2, the amplitude is 15. Function amplitude is 15 into sine of omega naught t d omega naught t. Okay? You can write it like this. Now take this 15 common, 60 by pi, and integration of sine is minus cos. Upper limit will be 0, and the lower limit will be cos alpha by 2. Okay? This will be the amplitude of the fundamental component. Okay? This will be the amplitude of the fundamental component. I hope you understood this. This is very important. Okay? 60 by pi cos of alpha by 2. Vishwanath, sir, 8 by pi na? No, it should not be 8 by pi. It should be 4 by pi. Okay? If you are applying quarter wave symmetry, then you have to integrate from 0 to pi by 2. But since 0 to alpha by 2, the function is 0. From 0 to alpha by 2, the function value is 0. Ft value, the current value is 0. So that's why I have not written that 0 to alpha by 2. I have directly written alpha by 2 to pi by 2. Alpha by 2 to pi by 2, you can say that the function is 15 ampere, and multiply by sine of omega naught t. You just integrate it from alpha by 2 to pi by 2, and you can calculate the value like this. So this will be my fundamental component. Now you can put the alpha is 45, alpha is 45. So now you can calculate its value. Now you calculate the decimal value. Okay. So the decimal value, please tell me what is the decimal value. 60 upon pi cos of 22.5. Cos of 22.5 degree. So you can easily calculate this. Okay guys, tell me what is the decimal value. I think it's very easy. No need to remember any formula. If you know the concept, you can apply directly. First you plot the wave shape of supply current, and then apply the quarter wave symmetry to calculate the fundamental component. So it's 17.64. Okay. Thank you, Chandrasekhar and yes, Yaswanath, thank you. So let's move to the next question, guys. I hope this is clear to everyone. Let's move to the next question. So the next question is a three-phase grid connected voltage source converter with DC link voltage of 1000 volt. So there is a voltage source inverter actually. There is a voltage source inverter. Voltage source inverter should be there, and the DC supply voltage is 1000 volt. VDC is 1000 volt. Okay. Now it says we have used the PWM technique. Okay. Switching used sinusoidal PWM. Okay. If the grid phase current is 10 ampere, okay, the phase current in the grid is, let's say, this is my three-phase output of the inverter. This is my three-phase output of the inverter, and the phase current is 10 ampere. This is the RMS value of the phase current. Let's call it, okay, for the time being, this is the phase current, and RMS value is 10 ampere, and the three-phase complex power supplied by the converter. This is the three-phase complex power supplied by the converter. Now you can calculate the apparent power from here. So the apparent power will be 4000 square plus 3000 square and take the root. So it will be 5000. This will be my apparent power. Okay. So this is my apparent power, guys. So we have calculated the apparent power. Then the modulation index used in sinusoidal PWM is, we need to calculate MA. Modulation index. Now let me tell you guys, obviously active power and reactive power and the apparent power has the meaning for fundamental component only. Reactive power is defined for fundamental, because for harmonic it is not defined actually. Okay? So if reactive power is given, it means the fundamental component we have to take, and this current, we can assume that this current is again fundamental component. Now this is the apparent power for three phase. Now what is the per phase power? So per phase power is 5000 divided by 3. This is the apparent power per phase, and we know that the apparent power is source voltage RMS per phase, source voltage RMS. How apparent power is 5000? Apparent power is active square plus reactive square and take the root. Okay, you'll get the apparent power, Chandrasekhar. 4000 square plus 3000 square and take the root of it, you'll get the apparent power as 5000. Okay, so this is the three-phase apparent power. Now whether you divide it by 3 or not, no problem. Let's take, this is the three-phase apparent power, and three-phase apparent power is root 3 VLIL. Root 3 VLIL. Okay, this is the formula for apparent power for fundamental component. For fundamental component, this is the formula for apparent power. Now I can say that VLIL is equal to 5000 by root 3. Okay, this is my VLIL, you can say. Now IL is given as RMS value of the fundamental component of the current. Though it is not written that this is the fundamental component, but we have no choice. We have to assume that this current is a fundamental phase current, and we have assumed that the load is star connected. So you can say this itself is a line current. So RMS value of the line current is 10. So you can say that the RMS value of the line voltage came out to be 5000 divided by root 3 into 10. Okay, this will be my line voltage. Just cancel it. So it will be 500 by root 3. This is my line voltage, guys. So we have calculated the line voltage. Now once you get this line voltage, remember this is the fundamental component. This is due to the fundamental component. Now what is the phase voltage? If you know the line voltage, then you can calculate the phase voltage. So the phase voltage came out to be divided by root 3. So phase voltage in across the voltage source inverter is 500 by 3. This is the phase voltage. Because this is the fundamental line voltage, divided by root 3, you'll get the phase voltage. So this is my phase voltage. Now this is the voltage due to fundamental component. Remember, this is the voltage due to fundamental component, and remember this is the RMS value. We have used the RMS value to calculate the complex power. Whenever you try to calculate the complex power, you use the RMS value of the line current and the line voltage. So we have calculated this line voltage, and this is RMS value. So we have calculated phase voltage by dividing it by root 3. Okay, so this is again RMS phase voltage. This is RMS phase voltage. What is the peak phase voltage? Peak voltage will be 500 root 2 by 3. Okay, this is my peak value of phase voltage, and the peak value of the phase voltage can be calculated as MA into VDC. Modulation index into VDC. Okay, if you remember, if you have understood the voltage source inverter, then you can directly calculate like this. Sir, if nothing mentioned about which inverter, half or full, then should I, yes, full converter, or moreover it's a three phase converter. In three phase we don't usually consider half wave converter, okay. We usually take full converter, okay. So, and voltage source inverter, it is already given. DC supply is given as 1000, so you can put 1000 here and you can calculate MA modulation index, okay. So the modulation index will be, MA will be equal to, put the DC value 1000, take this 1000 in the denominator, because we have calculated the fundamental amplitude, fundamental peak value of the phase voltage, and that fundamental value of the phase voltage is MA into VDC, okay. Now you take this VDC in the denominator, so you will get 1 by 3 root 2. Is it fine, guys? Is it fine? Please check it. 500, this is the peak value. MA into VDC is the peak value, okay. Once you get this, then you can calculate MA. Tell me, guys, what is MA? What is MA? Tell me, what is MA? What is MA? You can calculate MA. Tell me, what is this? MA. Everyone tell me. MA into VDC. Is it correct? My question is it correct or not? What is this? The value is 0.47. 0.47. Is it like this? Is it 0.47? Everyone tell me. Yeah, it's 0.23. It's half of that. Yeah, 0.47 or 0.23? Please tell me, everyone. 0.23. Is it 0.23 or 0.47? Tell me. Is it 0.23 or 0.47? Tell me. Is it 0.23 or 0.47? Tell me, guys. Yeah, it's 0.23. But the answer provided is, I think it's 0.47. Please check it. Answer provided is 0.47. Actually, what I did is, I made a mistake. Where I did make mistake, actually, the fundamental component of the peak value is not MA into VDC. It's actually MA into VDC by 2. MA into VDC by 2. Now, you will ask me, sir, why? Why it is MA into VDC by 2? Let me tell you. Let me tell you why it is MA into VDC by 2. Okay, and how to remember it. I'm not sure whether it is VDC by 2 or VDC, because I don't remember any formula. That's why let me try this. Let's say I have a three-phase converter like this, three-phase inverter like this. There are 3 legs, okay. There are 3 legs, and this is phase A, this is for phase B, and this is for phase C. And the supply is connected like this, okay. This is the 1000 supply. Now what you need to do is, you connect a capacitor here and one more capacitor here and make it ground. So with respect to ground, you can say that the upper point will be 500 or VDC by 2 and the lower point will be minus 500. Upper point will be, with respect to ground, the upper point will be 500 and the lower point will be minus 500, okay. Now if you look at this voltage, if you look at this phase A voltage, let's take this neutral grounded. Okay. So I have connected the neutral ground because nothing is given, so we can assume that the neutral is grounded, neutral is connected on both sides. Now if you look at this carefully, what is this voltage? Whenever the upper switch is connected, voltage is 500. Whenever the lower switch is connected, voltage is minus 500. So you can say that the voltage is fluctuating between plus 500 and minus 500, which is VDC by 2. So you can say that the phase voltage, fundamental phase amplitude of the fundamental component of the phase voltage is not MA into VDC. It is actually MA into VDC by 2. Why it is MA into VDC by 2? Because this phase voltage is fluctuating between plus VDC by 2 and minus VDC by 2, between 500 and minus 500. Okay, that's why I have to take 500 by 2. So this 2 will go to the numerator and the answer will be 0.47. Is it fine, guys? So this way you can calculate it. Is it correct, everyone? Tell me. Is it correct? Tell me, guys. I hope this is clear to everyone. Now let's move to the next question. I don't remember any answer, or I don't remember any formula, believe me, okay. And I haven't solved these questions previously, like there are some students who think that I have prepared these questions, or no, I am just applying the basic rules, okay. Because I don't need to solve these questions again and again, okay. I just believe on my basics. If it is so, then they use half bridge inverter, sir. No, half bridge inverter is used for, you can say, single phase, okay. But now they have connected full bridge now. At each leg you have plus VDC and minus VDC. Plus VDC by 2 and minus VDC by 2, okay. You have the voltage like this. Since the voltage is fluctuating between plus 500 and minus 500, it means VDC plus VDC by 2 and minus VDC by 2. So the fundamental amplitude will be MA into VDC by 2. So directly you can calculate from here MA, the modulation index you can easily calculate. Now let's move to the next question. The next question is this. In this question, a steady state current flowing through the inductor of a DC-DC buck boost converter is given in the figure. So we have the buck boost converter, and in the buck boost converter, the current through the inductor is given like this. If the peak to peak amplitude in the output voltage, if peak to peak amplitude in the output voltage of the converter is 1 volt, okay, peak to peak amplitude of the output voltage of the converter is 1 volt, okay. It means the ripple is given, output voltage ripple is provided to us. Then the value of output capacitor, we need to calculate the value of the output capacitor. Now the question is, how to calculate the ripple in the output voltage? First of all, I need to draw the buck boost converter. Now what is the, how the buck boost converter look like? Now you need to remember the diagram of buck boost converter. Look, this is my buck boost converter already drawn in some circuit, okay. So I'm using this, or maybe you can draw it, separately. So the buck boost converter is like this, okay. This is the buck boost converter we have. Now I don't remember any formula, just focus on your basics, just focus on your network theory, okay. In this question it is given the inductor current. The inductor current is given, this current is given, okay. Whenever the switch is on, the voltage is, you can say, VD, okay, and the current will rise, and whenever the switch is off, the voltage is V0, minus V0, opposite polarity voltage will be there, and the current will fall linearly, okay. So this is my buck boost converter, and across inductor, this is the through the inductor, this is the current. Now the question is, what is the ripple of the output voltage? Ripple is given as 1 volt. Now to calculate the ripple, I need to calculate this ID, diode current, IDT, because once you get this IDT, you can calculate the ripple. How? First of all, let's draw IDT. What is IDT? IDT is, if I somehow draw IDT, you know that whenever the switch is closed, the diode will remain off. Diode will remain off, the current will be 0. So from this point to this point, voltage across the inductor is plus VD, diode will remain off. Assume that this point is grounded now. If the switch is on, this point will be VD and this point will be minus V0. So you can say that this side is higher than this side, so diode will remain off. If diode remain off, then the current through the diode is 0. Current through the diode is 0, okay. Now, if the switch is off, then this current will be the current through the diode, okay. This current will be the current through the diode. I hope you understood it. So this is the current through the diode, and then again it will remain 0. So you can say that, let's start the wave from this point, let's call it origin, 0 point. This is 20 microsecond, this is 20 microsecond, and this is 30 microsecond, okay. Okay, this is 50 microsecond, because 20 plus 30 is 50, okay. So we call it 50 microsecond, 50 microsecond. So this is the wave shape of diode current. I have assumed that this point is origin. If this point is origin, then this length is 20 microsecond and this length is 30. So 20 plus 30 is 50 microsecond. So this point is 50 microsecond. So I have plotted the current through the diode. Now, if you look at this diode current IDT, that will be ICT plus I naught T. You can say that IDT is equal to I naught plus ICT. Okay. Now what is the average current of this diode? That is I equal to I naught. Average current of diode is called I naught. If somehow you subtract this average current, you'll get the ICT. Okay. You'll get the ICT. You'll get this current ICT. Once you get this ICT, you can easily calculate the ripple of this capacitor voltage, okay. Now how to calculate this average current? Average diode current. This I node is the average diode current. Now, average value you can calculate directly from here. How to calculate? Average is area under one period divided by the time period. So the one period length is 50 microsecond. This is the period length. So one period is 50 microsecond. One period length is 50 microsecond. And now I need to calculate the area under one period. Area, this area I need to calculate. How to calculate this area? We know that this height is 16 and this height is 12. So to calculate its area, it's very simple. This is a rectangle and this is a triangle. Now how to calculate its area? Area will be 12 into this length. This length is 30 microsecond plus what is the area of this triangle? This area of this triangle will be 1 by 2 into 4 into this length. This length is 30 microsecond. Okay, 30 microsecond. So 1 by 2 into this height into this length. Okay, you'll get this area. Is it correct, guys? Is it correct? Is it correct? I think it's correct. So 1 by 2 into 4 into this length is this triangle area. Divide by, this is the area, total area. Divide by the time period. Time period is 50 microsecond. That micro and micro and micro will cancel. So now you can calculate the average current. This 2 will be there. So you can say 12 into 30. So it will become 14 into 30 divided by 50. Okay. 42 upon 5 ampere. 42 upon 5 ampere is the average diode current. Is it fine, guys? We have calculated the average diode current. Average diode current is 42 upon 5. I think it's clear to everyone. So we have calculated the average diode current. Once you get this average diode current, then whatever this diode wave shape is, you just subtract this current. Na? You just subtract this current from this current, you will get the ICT. So if I plot ICT, let's plot ICT. Now how to plot this ICT? You just subtract this current. This current is, let's write in decimal form, 8.4. Okay, so this is 8.4 ampere. Now if I subtract this DC current, which is 8.4 ampere from this diode current, you'll get the capacitor current ICT. So ICT will be equal to this current minus this 8.4. So from 0 to 20 microsecond, the current will be minus 8.4 ampere, and then it will go like this, and then it will be like this. Okay, this will be the wave shape of capacitor current. Is it clear, guys? This is the wave shape of capacitor current. Once you get this wave shape of capacitor current, then it's easy to calculate the output voltage ripple or capacitor voltage ripple. How to calculate that? You can calculate this area. This area will represent the change in charge because the current is coming to the capacitor. If current is coming, then the capacitor plate is becoming more charged. Okay. Now what is the change in charge during this interval? You just calculate the area. You will get the change in charge. We call delta Q. Delta Q by C is called the voltage ripple, and the voltage ripple came out to be 1 volt. It is already given to us 1 volt. Okay, now C will be equal to delta Q by 1 volt because peak to peak ripple is already provided to us, na? And peak to peak ripple is whatever the change in current, whatever the change in charge, divide by the C, you will get the peak to peak ripple. Okay, now the change in charge will be this area. So this area will be 42 by 5 multiplied by 20 microsecond. 42 by 5 into 20 microsecond. So it will become delta Q by 1, you will get C because peak to peak ripple is already provided to us, na? 1 volt. So that peak to peak ripple is 1 volt, which is delta Q by C. Take the C on the right side and 1 on the left side. So you'll get this. So you can calculate, this is cancelled with 4. So it will be 168 microfarad. Is it fine, guys? Please check it. Is it correct? Tell me, guys. It's 168 microfarad. I hope you understood it. Is it fine? Everyone, tell me. Is it correct? So look at the question carefully. I don't remember any formula. I don't apply any formula. I just believe on basics. Okay. I just believe on basics. I know that once I get this diode current, I will subtract the average current from this diode current. I will get the capacitor current. Once I get the capacitor current will look like this. Then what I need to do is, I need to calculate this area or this area. This area and this area will be equal, okay. So whichever is simple to calculate, so this area is simple to calculate. That will represent delta Q. So delta Q by C will be called ripple voltage, okay, peak to peak ripple voltage. Peak to peak ripple is given to us now 1 volt. So you can put it 1 here and you can calculate the C value, okay. So it's very easy peasy. Is it fine, guys? Can I proceed? Everyone tell me. Okay, Chandrasekhar, please repeat this question again. If you have not understood, it means your basics are not good. So you can repeat the video or you can go the video back and then you can start from the beginning, okay, because I can't repeat every concept. Let me tell you the main points. The main points are, inductor current is given to us. From this point to this point, let's call it origin. Let's call it origin, 0 point. From 0 to 20 microsecond, current is rising. This current is rising. It means the VD is applied across it. The switch is on. And then from 20 microsecond to 50 microsecond, switch is off. It means the inductor voltage is opposite voltage. Diode is conducting. It means this is sorted here. So this opposite voltage will come across the inductor. It means current will fall because negative voltage is there across the inductor. So the current will fall. Now this is the current wave shape of inductor. Using this inductor current, what I can do is I can plot this diode current. How? We know that whenever the switch is on, diode will be off. It means there is no current through the diode. And whenever the switch is off, the inductor current is same as the diode current. So you can say that whenever the switch is off, this current will remain as the diode current. So we have plotted the diode current. We know that the diode current is made up of I naught and ICT. I naught is the average value of this diode current because average current will not pass through the capacitor. Average current will come via resistor. So you can say that the IDT is I naught T plus ICT. From here you can calculate ICT. You just subtract average current from the diode current. I naught is the average value of the diode current itself. So diode current wave shape we have already plotted. We can calculate the average value of this diode current, which came out to be 42/5. So now what I did is I subtracted this I naught current from this diode current. I subtracted the average component. Then I will get the capacitor current. So this is my capacitor current. In the capacitor current, this area and this area will be equal. Remember this point. So whichever area you can calculate, that will represent the change in charge. So this is represent the change in charge. Change in charge divided by C represent change in voltage. And change in voltage is given as 1 volt. Peak to peak ripple means minimum to maximum. What is the change? So the change voltage is 1 volt. So we can calculate this change in voltage is 1 volt and you can calculate C is equal to delta Q by 1. Delta Q is this change in charge. So you can easily calculate from here. I think it's easy peasy. Everyone can solve like this. Okay. Now let's proceed. Don't apply any formula. Don't remember any formula. Just basic concept you need to understand. Now let's come to the next question. So the next question is the circuit shown below. The input VI is a sinusoidal AC, okay. Input voltage is a sinusoidal AC having RMS value of 230 plus minus 20. RMS value of this is 230 plus minus 20%. Plus minus 20% of this, okay. The worst case peak to peak inverse voltage across any diode, okay. It's very simple. We need to calculate the reverse voltage across the diode. Whenever this diode is conducting, let's say, whenever this D1 is conducting, whenever this is sorted and this is sorted, you assume that this point is 0 and this point is VST. Whenever this D1 and D2 are conducting, then this VST will available here. This VST will available here and this will be 0. So you can say that since VST is positive and this is lower voltage, so this diode will remain reverse bias. Now, what is the maximum reverse voltage it has? What is the maximum reverse voltage it had? Maximum reverse voltage is 230 is the RMS value. 230 is the RMS value. So peak value will be 230 root 2. This will be the peak voltage plus minus 20% of this. Plus minus 20%. So what you can do is you can take 230 plus 20% of this is 20% of this is what is the 20% of this? This will be 230 plus 20% of this voltage is 46. So it will become 276. 276 is the RMS value. 276 is the maximum RMS reverse voltage across it. Now to calculate the peak value, what I need to do is I need to multiply with root 2. Or what you can do is you first multiply root 2 with this quantity. So if you multiply root 2, it will be the peak voltage, but plus minus 20 is also there. Na? So you just add plus 20%. So plus 20% is 40 root 2. Okay, 46 root 2. 20% of this is 46 root 2. So you can calculate the peak inverse voltage from here. Okay, it's easy peasy. You can just calculate this value or directly you can calculate this value. You will get the answer. So this will be my peak inverse voltage across the diode. It's simple. It's very easy. Whenever this diode D1 is conducting, this will be reverse biased. And how much voltage it will be reverse by VST. Because this side is 0, then this side will be VST. So this will be reverse biased by VST. Now what is the peak maximum value of VST? In the worst case, the maximum value of VST will be, you just calculate the maximum value, worst case maximum value. So in worst case will be positive. If you take positive sign, then worst case will occur. So what I did is 230 plus 20% of it, this is 46. This is the maximum RMS value across this diode. Multiply by root 2, you'll get the maximum peak value. Okay. So it's very simple. You just calculate the decimal value and put it here. Now let's come to the next question. In this question, what is given? A single phase full bridge inverter is fed by 235 volt DC. So here you have a 325 voltage DC. Sorry, 325 volt DC produces symmetric quasi square waveform AB as shown. Okay, so we have this waveform. To achieve the modulation index of 0.8. It is given that the modulation index is 0.8. Okay, modulation index is 0.8. The angle theta expressed in degrees should be. We need to calculate this theta. What is this theta? Modulation index is given as 0.8. Modulation index is given as 0.8. Okay. We need to calculate this theta. Okay. Modulation index is referred as the ratio of the peak of the fundamental component of AB to the applied DC voltage. Now, what is the fundamental component of this voltage? What is the fundamental? Because it is already given. MA is already provided. MA is the ratio of peak of the fundamental component of VAB. So, fundamental component of VAB. And peak of divide by applied DC voltage. Applied DC voltage is 325. Is it fine? So it's very simple. Applied DC voltage is 325. Now we need to calculate the peak value of we need to calculate this theta. How to calculate theta? First of all, we need to calculate, you can say, the fundamental component. What is the fundamental component in this? Look, this is pi by 2, this is theta, this is pi minus theta, I suppose. This is pi minus theta, okay? This point is pi minus theta. Now, if you draw the fundamental component will look like this. And using symmetry, if you plot this wave, before 0, the wave will look like this. Okay? The wave will look like this. So you can see that it's the odd wave, it's the odd signal. You can see that this signal is odd. If this is theta, this is minus theta. So this signal is odd and it contains odd half wave symmetry. So it means it has quarter wave symmetry. If this wave has quarter wave symmetry, then what we can do is we can apply the quarter wave symmetry to calculate the peak fundamental component. How to calculate the peak fundamental component? Let's calculate the peak value of this fundamental component. Using quarter wave symmetry, I can say that peak fundamental component will be 4 by pi from theta to pi by 2. From theta to pi by 2, the amplitude is 325 sine of omega naught t d omega naught t. This will be the peak value of the fundamental component. And this value came out to be 4 into 325 upon pi. And integration of sine is minus cos. Upper limit minus lower limit, it will become cos theta. So this is my peak value of the fundamental component of AB. Now, divide by 325. We call MA. MA is 0.8. So we can calculate theta from here. This is cancelled. So you can say that cos theta came out to be 0.8 into pi by 4. Is it fine, guys? Pi by 4. 0.8 into pi by 4. Is it correct? So you can calculate it from here. Please tell me what is the value. Please tell me, guys, what is this cos theta? And from here you can calculate theta in degrees. Everyone, please calculate theta in degrees. What is this theta? So it's very simple. It's very simple. We just applied quarter wave symmetry. If you don't know how to apply the quarter wave symmetry method, please watch my lectures. Okay, there are so many lectures on YouTube. You can search with my name, quarter wave symmetry by Asu Jangra, and you'll get those videos. You can watch it and then you can apply it. Okay, so using quarter wave symmetry, we can calculate the peak value of the fundamental component. Okay, this is the peak value of the fundamental component. Divide by the DC value, you'll get the modulation index. Okay, please tell me what is this cos theta. What is this cos theta and what is theta from here? Theta in degrees I need to plot, I need to tell. Tell me guys, what is this theta? Everyone please tell me. Please solve it. Calculate this theta or just apply, put it in the comment section because I want to change the question, and if you can calculate it, please put in the comment section so that those students who, okay, it's 51.5 or 51 degree. It's 51 degree, 51.05, it's 51. If your calculation is correct, Chandrasekhar, then I suppose this is correct. So this is 51. I don't know what the answer IIT provided, but this is the correct solution, okay? This is the correct method. Anyway, let's come to the next question. Let's come to the next question. In the next question, what is given is, consider the boost converter shown. This is the boost converter which is given in the diagram. The switch Q is operating at 25 kilohertz. Switching frequency is provided to us. And the duty cycle is 0.6. Okay, duty cycle D is given as 0.6. D is given as 0.6. Assume the diode and the switch to be ideal. Diode and the switch are ideal. Is saying diode and the switch are ideal. Under the steady state condition, the average resistance R in seen by the source. Okay, this is from this side, what is the input resistance seen? So the input resistance will be 15 divided by ID, average source current. Let's call this average current as ID, or the average inductor current you can say. So the average inductor current, you just calculate 15 divided by that average inductor current, you call input resistance. Now how to calculate this input resistance? How to calculate this average current? Input average current. Once you get this input average current, then it's easy to calculate. Now, first of all, this is the boost converter, and I need to check what is the average current here. If somehow you can calculate this voltage now, you will get the output current. If you get the output current, you can refer that current. You can calculate this current, this average current also. Now how to calculate this output current? Okay, we know that in boost converter, tell me, V0 upon Vd is 1 over 1 minus D. Is it correct? In boost converter, this is the relation, 1 over 1 minus D in continuous conduction, because we don't know whether the conduction is continuous or discontinuous. Okay, so I assume that the conduction is continuous. First of all, let's assume that the conduction is continuous, because we'll check it whether the conduction is continuous or discontinuous. We'll check that. Okay, so assume that the conduction is continuous, and V0 upon Vd is 1 over 1 minus D. If you don't remember how it came, if you don't remember this formula, then what you can do is, using inductor, you can apply that. First, you plot the inductor voltage. From 0 to T on, you can see that if the switch is on, the voltage across the inductor, this voltage is 15 volt or Vd. This voltage is Vd, okay? Now, from T on to T, this switch is off, so the diode is sorted. You can say that this side is V0, because I am assuming this is ground. So if it is grounded, this point will become V0 and this point is Vd. So the inductor voltage will be Vd minus V0, okay? So if the switch is off, you can say this is Vd minus V0, okay? And since V0 is greater than Vd, so it will be negative. That's why I have shown it negative direction. Now, this is the inductor voltage we have. I am assuming that the conduction is continuous. Now, what you can do is, you know that under steady state, the area of this VLT will be 0. So what you can do is, you can make this area 0. Vd into T on is dt, plus this Vd minus V0 into 1 minus d into T. Okay, T of is 1 minus d into T, and that is equal to 0. You put it equal to 0. This T is cancelled, okay, and you can see that the coefficient of Vd is d here and 1 minus d here. So 1 will be there, is equal to the coefficient of V0 is 1 minus d. So from here you can say that V0 upon Vd is 1 over 1 minus d. I think it's easy peasy. Okay, so if the conduction is continuous, you can say like this. Now, what is the duty ratio? Duty ratio is given as 0.6. duty ratio is given as 0.6. So if I take duty ratio 0.6, it will be 1 over 0.4. 1 over 0.4 is 2.5. It means the output voltage will be 2.5 times VD. Now 2.5. What is the 2.5 times of this? So it will be 37.5. So this voltage is 37.5. Is it correct, guys? Tell me. This voltage is 2.5 of 15. So 2.5 of 15 is, I think, 37.5. So we have calculated this current, this voltage, output voltage. Now, if this is the output voltage, what is the output current? So the average output current will be 37.5 divided by 10. So it will be 3.75 ampere. Is it fine, guys? Tell me. So it's 3.75 ampere. If this is the 7.35 ampere, then you can calculate this average current. What is this average current? What is this average current? We know that this ratio is same as ID upon I naught. Okay? If you know this current I naught, it is 3.75. So, and this ratio is 2.5. This ratio is 2.5. Take this I naught in this side. So ID is equal to 2.5 into 3.75. This is the average current of this inductor. This is the average current of this inductor. Good evening, Ashok. Tell me, guys, what is the average current? What is the average current of this inductor? So what we have done is, we have assumed that the conduction is continuous. Actually, we don't know whether the conduction is continuous or discontinuous. So we have to check. We have to check whether the conduction is continuous or discontinuous. How to check? I'll tell you, don't worry. But first of all, assume that the conduction is continuous. By assuming that the conduction is continuous, now tell me, if you assume that the conduction is continuous, then this relation will be valid. I know this VD, so we can calculate V naught. We can calculate V naught by just putting the value of D. Okay, so V naught came out to be 2.5 times of VD. It means 2.5 times of 15, that is 37.5. Okay, using 37.5, we calculate this I naught current 3.75. Now this I naught current I put in here and calculate the input side average current. Input side average current came out to be this 3.75 into 2.5. Now calculate this value. Please tell me, everyone, what is the decimal value here? Now look, if I calculate this in decimal, obviously I will be slow. Anyway, just calculate this value. What is this value? Tell me, what is this product? Tell me, guys, what is this product? What is this average current? Input side average current. Can you calculate? Can you tell me? Now whatever this average current is, 15 divided by this average current, you will get input resistance. 9.375. Okay, this is 9.375. 375 as per Chandrasekhar. Okay, thank you, Chandrasekhar. So this current came out to be 9.375. Is it correct, guys? Now to calculate this input resistance, what you need to do is 15 divide by this current. 15 divide by this average current, you will get the input average resistance. 1.6 ohm. Okay, so the resistance came out to be 1.6 ohm. But just wait. 1.6 ohm voltage. 15 divided by this 1.6 ohm. Now you have to wait. Why? You have calculated this. What's the problem? Problem is with this formula. Because we are not sure whether this formula is correct or not. This formula is correct if the conduction is continuous, and we have not checked it. We just by default we have applied it and then calculated it. So what we have to do is, we have to check whether the conduction is continuous or discontinuous. How to check it? How to check whether the conduction is continuous or discontinuous? It's simple. It's simple, guys. How to calculate it then? Okay, let's try to calculate. What you can do is, you assume that the conduction is just continuous. Assume that the conduction is just continuous. If you assume that the conduction is just continuous, the wave shape of the current will look like this. In just continuous case, this will be the wave shape of the current, and calculate its average value, inductor current average value. If this average current, inductor average current, is greater than this just continuous case, then the conduction is continuous. If this average current, which I have calculated by assuming continuous conduction, if this average current is less than this just continuous average current, then it will be discontinuous. It means you have to check whether the conduction is continuous or discontinuous, because you have applied this formula by default, by using the default condition. So default condition you can't apply all the time, na? You have to check it. Let's calculate this average inductor current in just continuous case. We have to calculate this average value. How to calculate this average value? First of all, calculate this peak value, IL peak. IL peak will be equal to initial current is 0 plus 1 by L integration 0 to T on voltage across inductor is VD. VD is 15 volt, 15 dt. So it will be 15 by L into T on. This is my IL peak. This is my IL peak. Now the average inductor current in just continuous case is area under one period divided by the time period. That will be the average value. So area under one period is 1/2 into IL peak. IL peak is 15 by L. 15 by L into T on. T on is dt. This is the 1/2 into IL peak into this length T divided by the time period. This is the average inductor current under just continuous case. Okay. So this is the average current, guys. So it will be 1/2 into 15 into D. D is 0.6. What is T? What is T? T is 1/25. 1/25 kilohertz. Kilo means 10 raised to power 3. And here in the denominator we have L. L is 1 millihenry. That milli is cancelled with this 10 raised to power 3. Now you can see that the average inductor current under just continuous case, that came out to be 15 into 0.3 divided by, this 2 is cancelled, na? I have written 0.3 here. 15 into 0.3 divided by 25. This is my average inductor current in just continuous case. And in continuous conduction, we have calculated this current. This is the average inductor current. It is greater than this value for sure, because this value is less than this value. It means if you have assumed the continuous conduction and if you have calculated this inductor current is greater than the just continuous case current. It means actually the conduction is continuous. This is the boundary condition for continuous and discontinuous conduction. This is the boundary condition. Okay. So under boundary condition, the average inductor current is this. If the actual inductor current is greater than the boundary current, then the conduction is continuous. It means we have done the correct calculation. Conduction is continuous. But let's say this current came out to be less than this value. Then all these calculation is not correct. I have to change this formula. I have to consider the discontinuous conduction, and in discontinuous conduction I need to calculate this average current. This voltage divided by this average current will be the input resistance. Okay. Now you are lucky. You are lucky that this continuous conduction case, if you started with the continuous conduction, the current came out to be this, and this current is actually greater than the just continuous conduction case current. That's why you are lucky in this case. And now conduction is continuous because this current is greater than this current. Conduction is continuous. This is correct answer. Okay. So I hope you understood it. Don't skip the question by just getting the answer, because it might be possible that the answer you get is not correct. Okay. So that's why we have checked this question. Maximum students do like this, but they don't check it. It might be possible that in some year, let's say in 2023, the question came like this again and the conduction is discontinuous. If the conduction is discontinuous, this formula will not be valid anymore. Okay, then you have to calculate again ID. ID will be somewhat different. And then you need to calculate the average resistance. I hope you understood, guys. I hope you understood this question. Anyway, we are lucky. Let's come to the next question. The next question is, consider the buck boost converter shown below. The switch Q is operating at 25 kilohertz. Okay, the switching frequency is given as 25 kilohertz. Okay, this is my switching frequency. And duty ratio is 0.75. D is 0.75. This is my duty ratio, guys. Assume diode and switch to be ideal. Under steady state condition, the average current flowing through the inductor. We need to calculate average current through the inductor. Okay. Okay. First of all, check whether the conduction is continuous or discontinuous. It is not given. So let's assume continuous conduction. Let's assume that the conduction is continuous, because it is not provided whether the conduction is continuous or discontinuous. So let's assume that the conduction is continuous. If the conduction is continuous, let's draw VLT first. Let's draw VLT. So if I draw VLT from 0 to T on, tell me guys, what is the voltage across inductor? From 0 to T on, this voltage is applied directly. If this voltage is applied directly, then you can say that this voltage is 20 volt. This voltage is 20 volt. Now from T on to T, this is off. So whatever current it has developed, that current will flow through the diode. So you can say that this voltage will come in parallel with this inductor. So the output voltage will be minus V0 now. Okay, output voltage will be minus V0. Okay, output voltage will be minus V0 now. Is it fine? Now what is this V0? How to calculate this V0? Assume conduction is continuous. If you have assumed continuous conduction, then we know that V0 upon Vd is D over 1 minus D. D over 1 minus D. In continuous conduction, we already know that. In buck boost converter, we have this relation. you put the value of D. D is 0.75. So 0.75 divided by 1 minus 0.75 is 0.25. So just calculate. This is 3. So this value came out to be 3. So V0 came out to be 3 times of VD. It means 60 volt. This is 60 volt. So the output voltage is minus 60. This is minus 60. Okay. T on. Now we have to check whether the conduction is continuous or so we assume that the conduction is continuous. We calculated the output voltage and then we plotted the inductor voltage. Inductor voltage is like this. Now inductor current. We know that inductor current during this interval, inductor current will rise linearly and then fall linearly. It will be like this. Is it fine, guys? This way you can plot the inductor current. First of all, how to check whether the conduction is continuous or discontinuous? Check this area and this area. If this area and this area came out to be equal, if this total area came out to be 0, it means the conduction is continuous here. Because let's say the conduction is discontinuous, then if in discontinuous conduction, this minus 60 will not be up to T. It will be 0 before this T. For some time it will be 0 if the conduction were discontinuous. But let's assume that the minus 60 is up to T time. If you are assuming that minus 60 is up to T and this area came out to be 0, it means conduction is continuous. I don't know how many of you have understood this point, because this is very critical point. I'm repeating this again. If the conduction is discontinuous, then the inductor voltage will be like this. This should be T. From this point to this point it should be 0. And I am assuming that up to this point it's minus 60. So this happens only in continuous conduction. In discontinuous conduction, it will be 0 before this T. It means this area and this area will be equal before this T point. Before this T point. Now, if it is becoming equal to this area becoming equal to this area up to T time, it means this minus 60 is up to T time, because this area is coming equal to this area only if I take this point equal to T. It means in continuous conduction. So let's calculate this area first. This area will be 20 into 3 by 4T. Okay. This area is 20 into 0.75. T on is dt. dt is this, na? And this area is 60 into minus 60 into 1 minus d into t. 1 minus d is 1 by 4 into t. Now check this area and this area. Just calculate it. It's 4 into, this is 5. Okay, and 15t. This is 15t, this is also 15t. It means this positive area become equal to negative area only if I take minus 60 up to t time. Then only it is equal. It is not equal if I take this point, this minus 60 up to this point, then this area and this area will not be equal. It is becoming equal to this positive area only if I take minus 60 up to t time. It means the conduction is continuous. This itself satisfies that the condition. So you can say that the conduction is continuous. Now, if the conduction is continuous, this formula is correct. If this formula is correct, this output voltage is 60. This output voltage is 60. Now, what I need to do is, I need to calculate the average current of the inductor. Inductor average current. How to calculate the inductor average current, guys? Tell me. How to calculate the inductor average current? This is the wave shape of inductor current. This is the wave shape of inductor current. Now, how to calculate? I think some term is missing. Something is missing. I think this resistance is missing. Can you tell me the resistance value? Wait a minute. Let me check the resistance value here, because I think something is missing in this question. So let me check the resistance value. Yeah, it's 10 ohm, guys. No. No. Please check the resistance value. I think the resistance value is missing in the original question also. Please check the resistance value, guys. I think this should be provided to you. This should be provided. Otherwise, let me check. Otherwise, whether we can calculate this or not. I don't think we'll be able to calculate it. Please tell me. Is it provided to you? This resistance value is provided to you, or this I is provided to you? Because if, let's say, this I is provided, then also you can calculate, na? I think this I, is it provided, this I value? I think this I value is provided. Tell me, guys. I think this value is provided. Please check. There is a correction in this question, I think. And this question is for gate 2021. Gate 2021. Please check the question and then I'll solve it. Okay, you can tell me in the chat section. I'll come to this question later because I think something is missing here. Okay, let's come to the next question. The next question is this on your screen, and in this question it is given that the single phase inverter is fed from a 100 volt DC source. There is a single phase inverter and it is fed from a 100 volt DC source, is controlled by quasi square wave modulation scheme and produce the output voltage Vt. So this is the output voltage. Okay, the angle sigma is adjusted to entirely eliminate the third harmonic. Okay, so it is saying that this sigma is adjusted such that there is no third harmonic. Okay, there is no third harmonic. What I need to do is, under this condition, if third harmonic is 0, then under this condition I need to calculate, under this condition, the magnitude of fifth harmonic component as a percentage of fundamental. First of all, I need to calculate this sigma such that the third harmonic came out to be 0. Once you calculate this sigma, then what I need to do is, then I need to calculate the fifth harmonic and the fundamental, and then take the ratio. Check the ratio. What is that ratio? We need to calculate that. So first, because this is pi, this is sigma, so you can say that this wave has quarter wave symmetry. If this wave has quarter wave symmetry, what is the fundamental amplitude, guys? The fundamental amplitude will be 4 by pi from sigma to pi by 2, 100 sine of omega naught t d omega naught t. Okay, and from here you can calculate, this will be 400 by pi. Integration of sine will be minus cos. Upper limit is 0, lower limit is cos sigma. Okay, so this will be my fundamental. Now let's come to third harmonic. In case of third harmonic, what you do is you just put 3 here. Okay, so it will be 4 by pi from 0 to pi by from sigma to pi by 2, and this will be 100 sine of 3 omega naught t d omega naught t. Okay, now if you calculate this amplitude, it will be 400 by 3 pi, and integration of sine will be minus cos of 3 omega naught t divided by 3. That 3 I have taken out. So minus cos 3 omega naught t. Upper limit is 0, minus lower limit, you'll get cos of 3 sigma. That is equal to 0. Okay. Now what is fifth harmonic component? Fifth harmonic component will be, you take this 5 here and 5 sigma here. So fifth harmonic component will be 400 upon 5 pi cos of 5 sigma. Okay, this will be my fifth harmonic. So this is fundamental over fifth, but the ratio is fifth as a percentage of fundamental. So you just revert it. So if you revert it, just cancel it first. Okay, if you revert it, it will be cos of 5 sigma divided by 5 cos sigma. Okay, this will be the ratio. Now we need to calculate this sigma. Sigma came out to be 30 degree. From here you can say that sigma came out to be 30 degree. Okay, because this will be 0 only if sigma is 30 degree. Third harmonic is 0 only if sigma is, okay. So sigma came out to be 30 degree. Put the sigma here in this equation. So it will be cos of 150 divided by 5 cos 30 and take the mode. Okay, this will be the answer. I hope you understood it. So it's very simple. Using quarter wave symmetry, what I did is I calculated the amplitude of third harmonic component. So I calculated the amplitude of third harmonic component by this expression, okay, and this will be 400 by 3 pi cos of 3 sigma, make it equal to 0, sigma came out to be 30. The fundamental component is this. Fundamental component is 400 by pi cos sigma. Third harmonic is this. Now the fifth harmonic is, according to analogy, you just take it 5 here and take it 5 here. So this will be the fifth harmonic amplitude. So what you need to do is you need to invert it, because fifth to fundamental is asked. So if you can invert it, then you can say that it will be in the numerator. So cos 5 sigma upon 5 will be in the numerator and cos sigma will be in the denominator. You can calculate like this. Sigma you can put 30 degree here. So cos 150 divided by 5 cos 30. It's very simple. Okay. So this way you can calculate this ratio. This ratio is asked in this question. I think it's easy peasy. Okay. In the previous question, Raju is saying that R is 10. Okay. This R is 10 ohm. Is this correct, guys? This R is 10 or not? Please verify this, whether this R is 10 or not. Whether this R is 10 or not. This is GATE 2022 question, I think. GATE 2021 question, yes. It's GATE 2021 question. Please check whether this resistance is 10 ohm or something else. Please verify this so that I can proceed this question. But before that, I mean, we can solve this question like this. It's a Fourier based question. So it's simple Fourier analysis I have done. Using quarter wave symmetry, you can calculate, okay? Yes, the previous question was GATE 2021. Please check. This R should be provided, I suppose, because otherwise you can't calculate that, okay? Whether this I is provided or this R should be provided. Please check. Something is missing in this question, huh? So let's come to the next question till then, so that everybody can, I mean, the other student can verify it. Raju verified that R is 10. So is there any student who can watch it, who can see that 2021 question and verify whether there is 10 ohm or some I is there? Please verify that. Let's come to the next question till then. So if you look at this question, a single phase full bridge rectifier fed from 230 volt 50 hertz sinusoidal source. So we have a full bridge rectifier, okay? Full bridge rectifier, 50 hertz supply is there, sinusoidal supply, a series combination of finite resistance R and very large inductance L. The two most dominant frequency component in the source current. We need to check what is the frequency of the source current, okay? So, what are the components which will dominate in the source current? So it's very simple. So the circuit is like this. So you have converter and load is RL. In RL load, L is very high such that the current is constant. So let's assume that the current is constant, I naught. If you plot the supply current, the supply current will be like this, a square wave. Supply current will be a square wave. Whenever this D1, D2 conduct, in 0 to pi, D1, D2 will conduct and the current will be positive, okay? Supply current will be positive. Whenever this D3, D4 will conduct, the supply current will be negative, okay? So you can say that this will be the supply current, I naught and minus I naught. Now what is the frequency? What is the frequency? What is the dominant harmonic? In this, it contains odd harmonic. So fundamental, separate the fundamental. Other than fundamental, we have third and fifth. And third harmonic has the frequency 150 and the fifth harmonic has the frequency 250, okay? So these are the dominant harmonic, okay? Okay, so in the previous question, in this question, it is given that this is 10 ohm, okay? Now it is easy to solve. So what I did is, in this question, it is given that frequency is 25 kilohertz and duty ratio is 0.75. What I did is I plotted this inductor voltage first. Once you get this inductor voltage, then the positive area become equal to negative area only if you take this V naught, only if you take this minus V naught up to this time t. If you take this V naught before the t, then the conduction will be, this area will not be equal to this. You can't take like this, okay? So you have to take this minus 60 up to this t. And what is minus 60? Minus 60 is output voltage using this expression. Using this expression, you get the output voltage as minus 60. So it means the conduction is continuous because this positive area become equal to negative area only at time t. It means the conduction is continuous. If the continuous conduction is there, then this will be the current wave shape of this inductor. Now I need to calculate the average value of this inductor current. This resistance is given as 10. If this resistance is 10 and this voltage is 60, then you can say that this I must be equal to 6 ampere, okay? This I must be equal to 6 ampere. Now, if this is the 6 ampere, output current is 6 ampere, then I can say that if V naught upon Vd is d upon 1 by d, then Id upon I naught is also d upon 1 by dc, okay? Now, if you know this I naught value, if you know the average current of I naught, you can calculate the average current of Id. So, Id will be equal to I naught into d over 1 minus d, so into 3. So, it will be 18. So, you can say that this average current is 18 ampere. Is it fine, guys? This average current is 18 ampere, this average current is 6 ampere, and now the inductor average current will be sum of these two average current, that is 24 ampere. Okay, now the question is why? Why it is the sum of this current and this current? Remember, if you plot this inductor current is like this. Now, if you plot this switch current or the supply current will be there only if the supply current will be equal to inductor current only if the switch is on. It means if you plot the supply current, then the supply current will look like this. Let me plot it here. 0 to t on, the supply current will be like this. If the switch is on, the inductor current will be same as the supply current, okay? So the inductor current is like this. So this will be supply current, and when the switch is off, the supply current will be 0. And then the supply current will be same as the inductor current. This will be the supply current. Now what is the diode current? Whenever the switch is off, then the inductor current is same as the diode current. It means if I plot the diode current from 0 to t on, diode is off. So you can say the diode current is 0, and from t on to t, whatever this inductor current is, same as the diode current. So the diode current will look like this, okay, and then 0 and then like this, okay. So this will be the diode current. So you can see that the inductor current is sum of this supply current and this diode current. Then only you will get the inductor current. So if you need to calculate the average value of this inductor current, what you need to do is, you need to calculate this average value of this diode current, which is equal to I naught, and the average value of this supply current, which is equal to 18. So if you have calculated these average values, you just add them, you'll get the overall average value of the inductor, which came out to be 24 ampere. Okay, so it's very simple question. And conduction was continuous. That's why we will able to do it. That's why we will able to apply this formula. Otherwise, this formula is not applicable. We have to change the formula. Okay. Now, let's come to the next question. Next question is this. Question number 13. Okay. So, this question, a double pulse measurement of an inductive loaded circuit controlled by IGBT switch is carried out to elevate the reverse recovery characteristics of the diode D, represented approximately as the piecewise linear plot of the current versus time at the diode turn off. Okay, so actually this is the circuit which is provided to you. You can read the statement. A double pulse measurement of a inductive loaded circuit. This is inductive load. Okay, controlled by IGBT switch is carried. So we have a freewheeling diode, and in freewheeling diode we have this L inductance. You can say it is a parasitic inductance due to wiring of the circuit, due to wire has some inductance now. So we call it parasitic inductance, which is connected here. The point of the plot indicated your choice by entering 1, 2, 3, 4. Okay, these are the points at which the IGBT experience the highest current stress. At which point the IGBT will get the highest current stress. Okay, so if you look at this carefully, from this point, at this point the diode current is, this is the diode current, guys. The diode current is only in this direction. No? So you can say that diode current is 1 here, constant current. So this voltage is 0, this voltage is 0. If I assume 0 volt here, this voltage will be 0 here, and you can say that this is 0, this is 0. So current is freewheeling, and let's say the current is constant. He is saying that the current is constant. Let's assume that the current is constant, and at the upper point we have VST, the source voltage. Now the current is linearly decreasing. Now if the current is this current is decreasing, according to this current, this should be the polarity of the voltage across inductor. Now if this is the polarity of the inductor, if this is the polarity across the inductor, then this voltage is L di by dt. Now since di by dt is negative, from this point to this point di by dt is negative. If di by dt is negative, then the polarity will change. This will be the polarity here. So I will get this polarity. It means at this instant, at this point, during this range, since diode is conducting, so you can sort it, and this voltage will be somewhat positive. You will get positive voltage here. You'll get positive voltage here. Is it fine? Up to this point, you'll get the positive voltage here, and the current is flowing in opposite direction. Current is positive in this direction, but up to 2 seconds, the current is in this direction. After that, current has reversed its polarity. Current is flowing like this. Current is flowing downward. Okay. Now the current is flowing downward up to from 2 to 3. The current is flowing downward. Okay, current is flowing downward. Now, if you look at this point, what will happen is, at this point, or maybe just after this point, you can say that this polarity L di by dt has changed. Current is negative. It means current is going like this. So the polarity should be, wait a minute. So the polarity of L di by dt, since the at point you can see that, wait a minute guys, what is this? Oh yes. So now you can see that the current is negative. If the current is negative, it means the current is coming like this. If the current is coming like this, then if the current is coming like this, and it is, since it is negative, that's why I have taken the current like this. Now L di by dt, according to the current, the polarity should be like this, L di by dt, and just after 3 you can see that the slope become positive. If the slope become positive, then this voltage will also become positive. At this point we have the positive voltage. You can see that the current is negative. Negative means current is coming like this, and the slope is positive now. So this is the voltage. So now we have the positive voltage here, and the current is coming like this. Now what you can say is, you can say that if let's say IGBT is turning on at this instant, this current is downward and this current is also, you can say, if this is on, this has to supply this current. Na? So you can say that the load will also demand some current. The load will also demand some current. Okay, the load will also demand some current, and you can say that the IGBT will be under highest stress of the current. At this instant, it has to supply this current also and this current also. Okay, so I hope you understood. And at this instant, this current is maximum. So the point number 3, it's just an idea. Okay, the point number 3 is the maximum stress point. At point number 3, the current is negative and going like this. Okay, going like this. And if the load current is also like this, then the IGBT has to supply this current plus this current. So it is under the maximum current stress. Okay, this way you can solve it. Let's move to the next question. This question is wrong. This question is MTA. This question is wrong. Now you'll ask me, sir, why this question is wrong? So I have done MATLAB simulation on this. You can search this wrong questions in GATE 2020. GATE 2020. Please search this. Wrong question in GATE 2020 by Asu Jangra. You search this, and I have done a MATLAB simulation on this question, and I found this is wrong, and we have sent the MATLAB simulation result to IITs also. So IIT give it marks to everyone. Okay, give the marks to everyone. So this question is wrong actually. So no need to discuss about this. Why it is wrong, we'll discuss in some other lecture. Okay. Let's come to the next question. In this question, a single phase full bridge fully controlled thyristor. There is a fully controlled thyristor. So there is a fully controlled thyristor like this. So we have fully controlled thyristor. Okay. So it is like this. We have fully controlled thyristor, and in fully controlled thyristor, the load is of 10 ohm resistance in series with very large inductance. Okay. So we have 10 ohm resistance and very large inductance. L tends to infinite, let's say. Okay. The rectifier is fed with 230 RMS voltage with 50 Hertz supply. Okay. So this is the supply, sinusoidal source through the cable, which have negligible internal resistance and total inductance of. Okay. So we have some source inductance. Here we have some source inductance. And the source inductance is 2.28 millihenry. 2.28 millihenry is the source inductance. If the thyristor are triggered at an angle alpha, alpha is given as 45 degree. This is my alpha. Now the overlap angle I need to calculate. What is the overlap angle? Okay. Now how to calculate the overlap angle? It's very simple. It's very simple. This is my supply voltage. At alpha, you have triggered T1 and T2. You have triggered T1 and T2. It means before alpha, T1, T2 were not conducting. Actually, T3, T4 were conducting, and the current was constant because L is very high. So let's assume that the current is constant. If the current is constant, then the constant current was flowing through T3 and T4. Is it fine, guys? T3, T4 were conducting. So you can say that the current was flowing through T3, T4. Okay. So now you can say that before alpha, the current was negative. Supply current was negative. Supply current was negative because current was coming like this. Okay. Now at alpha, what happens is you fire T1, T2. If you fire T1, T2, then current will start rising like this. Okay. From alpha to alpha plus mu, up to alpha plus mu, there will be overlapping. There will be overlapping, and current will start from minus I naught to plus I naught. Okay. Minus I naught to plus I naught, current will go like this. So there will be overlapping at this instant. Now, if there is an overlapping, then all the 4 thyristors are conducting. If all the 4 thyristors are conducting, then you can say that the circuit is like this. The circuit is like this. All the 4 thyristors are conducting during overlapping interval. Okay. All are sorted, and here you have constant current I naught. Okay. Now, the question is, this current is developing and this current is decreasing. During overlapping, the source current is changing its polarity. It means this current is increasing. These 2 diode current is increasing, and these 2 diodes current, thyristor currents are decreasing. So if you have studied effect of source inductance, according to that concept, I can say that this current is I mu and this current is I mu. And I mu is changing from 0 to I naught. You can say that this thyristor current and this thyristor current is increasing from 0 to I naught. And this thyristor current will become I naught to 0 because this I naught, I mu is opposite to this current. Now, previously it was current in this thyristor current was like this, and in this thyristor current was like this. So you can say that this I mu is opposite to this I naught. Na? Similarly, this I mu is opposite to this current. So this diode current, this thyristor current is decreasing. This current is also decreasing. This current and this current is increasing. So now you can apply the KVL. Now you can apply the KVL in this circuit. If you apply the KVL, then you can say that VST minus this drop is Ls d by dt of 2 I mu minus I naught is equal to 0. Okay, this is my KVL. So according to this KVL, I can say that Vs is Vm sin omega t is equal to, take this 2 I mu on this side, so 2 Ls d I mu by dt. Take this 2 Ls in the denominator, so you will get d I mu integration from 0 to I naught is equal to Vm sin of omega t upon 2 Ls and dt. Divide with omega and multiply by omega and integrate on both sides. Okay, here you integrate from alpha to alpha plus mu. Okay, and here you integrate with respect to I naught. So if you integrate it, you will get I naught is equal to Vm by 2 omega Ls, and here the integration sign is minus cos, upper limit minus lower limit. So if you apply upper limit minus lower limit, you will get cos alpha minus cos of alpha plus mu. You will get like this. So from here you can calculate mu value, overlapping interval. But the problem is I naught. We don't know this I naught. Now how to calculate this I naught? If somehow we can calculate this I naught, we can calculate this mu. If you remember this formula, then it's very good. You can directly use this formula. But the problem is I naught. We don't know this I naught. How to calculate this I naught? How to calculate this I naught? To calculate this I naught, what I need to do is I need to calculate the average output voltage. Divide by the resistance. I'll get the output current, average output current. Now what is the average output voltage? Now the average output voltage will not be equal to 2 Vm by pi cos alpha. No sir. It will be average output voltage with source inductance 2 Vm by pi cos alpha minus cos of alpha plus mu. Minus cos of alpha plus mu. This will be the average output voltage, guys. This will be the average output voltage. Okay. This will be the average output, cos alpha minus cos of alpha plus mu. Wait a minute, let me check. Minus or plus? I think this 2 will not be there and the sign will be plus. Okay. Wait a minute. This 2 will not be there and here you have plus sign. Yes. Wait. Oh. Here you'll have the plus sign. Okay, this will be the average output voltage, guys. Vm by pi cos alpha plus mu. Now we don't know this mu. If you don't know this mu, how to calculate this average value? So what I need to do is we need to calculate this mu, na. Then only you will get this output average voltage. Look. From here, what I can say is I can calculate this cos of alpha plus mu. And I put this cos of alpha plus mu here. Okay, then I will get the average output voltage. Let's try this. So if I take this 2 omega Ls I naught on this side, and so it will be cos alpha minus cos of alpha plus mu will be equal to 2 omega Ls I naught by Vm. Okay, 2 omega Ls I naught by Vm. From here I can calculate this cos of alpha plus mu. So cos alpha plus mu came out to be cos alpha minus 2 omega Ls I naught by Vm. This is my cos alpha plus mu, guys. This is my cos alpha plus mu. Once you get this cos alpha plus mu, you can put it here, okay, and you will get the average output voltage. So the average output voltage will be, let me write on this screen, V naught T average will be equal to Vm by pi into cos alpha plus, what is this cos alpha plus mu? Cos alpha plus mu is equal to cos alpha minus this. So it will be doubled and minus minus, what is this, 2 omega ls I naught, 2 omega ls I naught divided by Vm. Okay, so you can write like this. I hope it is clear to everyone. Please check it. So what I have done is, I have calculated this cos alpha plus mu. Cos alpha plus mu came out to be this. From here, the cos alpha plus mu I have calculated, and I put this cos alpha plus mu in this. So this will be my V naught average now. This will be my V naught average now. Okay. Now what you need to do is, you can calculate I naught. We know that I naught is equal to whatever this average voltage divided by R. R is 10. So 1 by 10 into Vm by pi, 2 Vm by pi cos alpha minus 2 omega ls I naught by pi. Okay, this will be my I naught. Now take this I naught term on this side, calculate the I naught first. Once you get this I naught value, because here you can calculate I naught now, because omega is known, ls is known, Vm is known, alpha is known, everything is known, I naught is unknown. First you calculate I naught from here. Once you get I naught from here, what you can do is, you put I naught in this expression, you will get mu. So it's a lengthy question. It's a lengthy question, but I told you what is the process. What is the process and how to calculate this. Now you do it, okay? Because I have already taken 2 hours approximately. So better we stop the class here, because the remaining question I'll take in some other class, maybe in the next class. So let's stop it here, because there are some 4 or 5 questions which are remaining. So actually there were total 25 or maybe 26 questions were there. Na? So I have solved almost 16 questions, guys. Or maybe this question, this 15th question, I'll repeat it again, because it has so much calculation. So we will do these calculations in the next class, okay? So let's stop it here, because the remaining 10 questions or maybe 11 questions I'll take in the next class, okay? So I'll adjust one more class, and in that class I'll take those questions. So let's stop it here. I hope you enjoyed this session. So thank you for showing interest in this class, guys. So I have almost solved 50% of the PYQs from power electronics from last 5 years. In the next class I'll solve other 11-12 questions which are left behind. So we'll try to solve those questions, okay? So let's stop it here, and see you in the next class. So take care, bye, take care guys, and I hope you enjoyed. So पढ़ते रहिए, मुस्कुराते रहिए. Next time मिलेंगे दोस्तों, ठीक है? अपना ख्याल रखिएगा. तो मिलते हैं फिर next time. Thank you and take care. Bye.